Hello friends, welcome to the NPTEL online certification course Retrofitting and Rehabilitation of Civil Infrastructure. Today we will discuss Module D. The topic for Module D is fiber reinforced polymer composites and its characteristics. In the previous lecture, we have discussed the properties of different types of fibers and resins and their stress strain relationships, the properties of fiber reinforced polymer composites and their stress strain relationships, the advantages and limitations of fiber composites and its various application in different industries. In today's lecture, we will discuss the micromechanics of composites. In micromechanics of composites, we will discuss how we can determine the elastic moduli of composites by knowing the properties of the different phases, that is the fiber and the matrix. In a composite, the properties depend significantly upon the properties of fibers and matrix and their relative proportions. The relative proportions may be in terms of weight fractions or volume fractions in a composite. The properties depend significantly on the amount of fiber and matrix in a composite. Micromechanics of composite is the analysis of the estimation of load sharing by fibers and matrix based on their properties and the micromechanical aspects of their volume weighted relationships. So, in micromechanics of composite, we determine the elastic properties of the composite at the fiber level. So, it is the analysis at the fiber level, and by knowing the properties of the individual fibers and the matrix phases and their relative proportions in terms of their weight and volume, the properties of the composite is determined. In determining the properties of composite, there are several basic assumptions. The assumptions are that both fiber and matrix are homogeneous and isotropic. The composite may not be homogeneous because of the presence of fibers, but individual fibers are homogeneous and isotropic, and also the matrix part. The fiber, matrix and the resulting composite exhibit linear elastic behavior. We have seen in the earlier lecture that the stress strain relationship of fiber and matrix are generally linearly elastic and the resulting composite also. Fibers are uniform, they are regularly spaced within the composite and perfectly aligned within the composite. The matrix is free of voids. The fibers are placed within the matrix and the matrix is free of voids, and there is perfect bond exists between the fiber and the matrix, so that no slippage occurs at the interface. So, we assume that the fibers are perfectly aligned, the matrix is free of voids and there is no delamination, no slippage between the fiber and the matrix, and the lamina is in a stress free state. To determine the volume and weight fractions, there are several terminologies that are used. Capital V with suffix C is the volume of composite. For composite, we use the suffix C. For fiber, it is the F that is used, and for matrix, we use M as suffix, and the volume, weight and density are denoted as V, W and rho respectively. So, the weight of composite is denoted as Wc, the volume of fiber is denoted as Vf, and the density of matrix is denoted as rho m, and similarly the other fractions. Now, we need to determine the fiber volume fraction, the fiber weight fraction, the matrix volume fraction and matrix weight fraction. So, this is an idealization of a unidirectional composite. We can see here this is the composite where there are two phases, one is the fiber phase and the other is the matrix phase. Though the fiber is suspended into the matrix more or less uniformly, but however, here to distinguish the two phases, it is shown schematically as this part is fiber phase and this part is the matrix phase. So, this is an unidirectional composite where the fibers are aligned along this axis. The properties are denoted as the weight of matrix is Wm, the volume of matrix is denoted as Vm and the area of the matrix is denoted as Am. Similarly, for the fiber phase it is Wf, Vf and Af. Now, the volume of composite that is Vc can be written as Vf plus Vm, that is the volume of fiber plus the volume of matrix, and we have assumed that there is no void. So, the volume of composite is the summation of the volume of fiber and the volume of matrix. Now, the volume fraction of fiber and the volume fraction of matrix is written as this. Small Vf is the volume of fiber by the volume of the composite. So, it is the volume fraction of fiber that is equal to the volume of fiber by the volume of the composite. Similarly, the volume fraction of matrix is the volume of matrix divided by the volume of the total composite. Now, if we add the two volume fractions of fiber and matrix, that is Vf plus Vm, we can see that it is equal to 1. So, Vf plus Vm, that is the volume fraction of fiber and the volume fraction of matrix is equal to 1. Similarly, we can write the weight fraction of the two phases. So, the weight fraction of fiber is small Wf, it is denoted as small w suffix f. So, it is the weight of fiber divided by the weight of composite. Similarly, the weight fraction of matrix is the weight of matrix by the weight of the composite. So, if we add the two weight fractions, that is Wf plus Wm, we get 1. So, the volume fraction of fiber plus volume fraction of matrix is equal to 1 and the weight fraction of fiber and the weight fraction of the matrix is also equal to 1. Now, the total weight of the composite is the total weight of the fiber plus the total weight of the matrix. So, we can write the weight in terms of density and volume. So, rho c into Vc for the composite is equal to the rho f into Vf for the fiber plus rho m into Vm for the matrix. So, dividing both sides by the volume of composite, we get rho c, that is the density of the composite, is equal to rho f into the volume fraction, because Vf by Vc is the volume fraction of fiber, plus rho m into the volume fraction of the matrix, which is Vm by Vc. So, by knowing the volume fraction of fiber and the volume fraction of matrix and also the densities of the two, we can get the density of the composite with this equation. Similarly, by replacing the volumes in terms of weights and density in equation 1, this is the equation 1. In this equation, we are replacing the volume with weights and density. We get Wc by rho c for the composite is equal to Wf by rho f plus Wm by rho m, and dividing both sides by the weight of composite, we get 1 by rho c is equal to Wf by rho f plus Wm by rho m. So, the density of the composite can also be written in terms of their weight fractions and the densities of fiber and matrix. Here in this equation, the density of the composite can be written in terms of their volume fractions, and here it is written in terms of their weight fractions and also with the densities of fiber and matrix. Now, we can also write Wf, we can also write Vf by Wf, that is volume fraction by weight fraction, which is equal to the total volume of fiber by the total volume of composite divided by the total weight of the fiber by the total weight of the composite, and that gives us rho c by rho f. So, we can write the volume fraction of fiber is equal to Wf into rho c by rho f. Similarly, Vm, that is the volume fraction of the matrix, is equal to the weight fraction of the matrix into rho c by rho m. So, these are the two relationships that are used in the subsequent analysis, that is the weight fraction and the volume fractions are related. So, we can get the relationships between the volume fraction and the weight fraction of the fibers and also the matrix. Now, here are some important notations that we need to know for further analysis. ECL is the elastic modulus or Young's modulus of the composite in the direction of the fiber. C denotes the composite and L denotes the longitudinal direction. So, it is the modulus of the composite in the direction of the fiber. Similarly, sigma CL is the strength of the composite in the direction of the fiber. Epsilon CL is the strain in the composite in the direction of the fiber. ACL is the cross sectional area of the composite perpendicular to the direction of the fiber. Similarly, the transverse direction ECT is the Young's modulus of the composite in the transverse direction. Sigma CT is the composite strength in the transverse direction. Epsilon CT is the strain in the composite in the transverse direction, and ACT is the cross sectional area of the composite parallel to the direction of the fiber. There are some more terms. Similar notations are used for fibers as well as matrix. For example, EF is the modulus of the fiber in the direction of the applied load, and sigma F is the fiber strength in the direction of the applied load. Similarly, EM is the modulus of the matrix in the direction of the applied load, etc. Now, we will discuss how to determine the elastic modulus of the composite along the direction of the fiber. So, it is the longitudinal strength and stiffness of the composite, and it is along the direction of the fiber. So, here is an idealized schematic diagram. This is a unidirectional composite member. We can see here the two phases are shown differently. This is the fiber phase and this is the matrix phase. The fibers are aligned along this direction and this is the matrix. The composite is of length L. Though the fibers are suspended into the matrix, however, for the analysis purpose, we are showing it in this way, the two different phases of the composite. The composite is subjected to a load, you can see here a load that is PC, a tensile force PC, and due to this tensile force the composite undergoes deformation, and this is the deformed section of the composite. So, it elongates and this is the deformed section. The assumptions for the analysis is that the rod extends uniformly with no delamination between the matrix and the fiber. So, here we assume that though it is subjected to loading, the composite extends uniformly and there is no delamination, no slippage between the fiber and the matrix. The transverse sections that were plane before bending remains plane after bending. This indicates that the strain in the matrix and the strain in the fiber are the same. So, the epsilon CL, that is the strain in the composite, is equal to the strain in the fiber, and also that is the same strain is applied on the matrix part. So, epsilon F is equal to epsilon M is equal to epsilon CL, and this is equal to delta L by L. This part, the deformation is the delta L and the strain is equal to delta L by the L, that is the original length of the composite. Now, the elastic modulus can be written as stress by strain. So, for the fiber EF, that is the elastic modulus can be written as sigma F by epsilon F. So, sigma F is equal to EF into epsilon F. Similarly, for the matrix, EM is equal to sigma M by epsilon M, or sigma M can be written as EM into epsilon M. Now, the load is taken by the entire composite and that load is shared by the fiber part and the matrix part. So, the total load PC is equal to the load shared by the fiber, which is PF, plus the load shared by the matrix, which is PM. So, PC is equal to PF plus PM. Now, PC can be written as sigma CL into ACL, the stress into the cross sectional area, and this is equal to the load shared by the fiber, that is sigma F into AF plus sigma M into AM, which is also written as in terms of the strain, that is EF into epsilon F into AF plus EM into epsilon M into AM. We are replacing the stress by the strain and the elastic modulus. Since the strain is the same in the fiber as well as in the matrix, so we can write that sigma CL into ACL is equal to EF into AF plus EM into AM whole is multiplied by epsilon CL. That is written here, sigma CL into ACL is equal to EF into AF plus EM into AM into epsilon CL, which is the same for fiber and matrix. Now, by changing this epsilon CL here, we are putting this epsilon CL in the left side and ACL in the right side, we get ECL. This is ECL is equal to EF into AF by ACL plus EM into AM by ACL. This can also be written as this equation, equation 21, by multiplying the length of the composite in the denominator as well as in the numerator in both these components of fiber and matrix. So, this AF into L is nothing but the volume of the fiber, AM into L is the volume of the matrix, and ACL into L is the volume of the composite. So, this is the volume of fiber and this is the volume of composite. So, this gives the volume fraction of the fiber. So, this is the volume fraction of the fiber, which is VF. Similarly, this is the volume fraction of the matrix, which is written as VM. So, ECL can be written as EF into VF plus EM into VM. Equation 20, this equation can also be written as sigma CL is equal to sigma F into AF by ACL plus sigma m into Am by ACL, and that can be written as sigma f into Vf, because Af by ACL is also the volume fraction. If I multiply L on numerator and denominator, that becomes the Vf. So, this is equal to sigma f into Vf plus sigma m into Vm. So, ECL can be written as Ef into Vf plus Em into Vm, that is the elastic modulus of fiber into the volume fraction of fiber plus the elastic modulus of the matrix into the volume fraction of the matrix. Similarly, we have derived sigma Cl, that is the stress in the composite, is equal to the stress in the fiber sigma f into the volume fraction plus the stress in the matrix into the volume fraction. This is known as rule of mixture. So, if we know the volume fraction of the individual components, that is Vf or Vm, and the properties like say Ef or Em, or here it is sigma f or sigma m, we can find out the properties of the composite, and this is the rule of mixture. So, to determine the elastic modulus of composite, the rule of mixture can be applied, and by knowing the volume fraction of the fiber and the volume fraction of the matrix and their elastic modulus, we can find out the elastic modulus of the composite in the direction of the fiber. Similarly, the stress in the composite can also be obtained from the rule of mixture. Now, the fraction of the load carried by fibers in the unidirectional lamina can be determined as Pf by Pc. Pf is the load taken by the fiber and Pc is the load taken by the entire composite. So, this way we can write it, this is equal to sigma f into Vf by sigma f into Vf plus sigma m into Vm, and Vm can be written as 1 minus Vf since there is no void. So, we can write it in this way also. So, by knowing the volume fraction of the fiber and the matrix and their elastic modulus, we can find out the fraction of the load carried by the fiber. This equation can also be written as ECL is equal to Ef minus Em into Vf plus Em, because Vm is 1 minus Vf. So, we can write equation 25 as ECL is equal to Ef minus Em into the volume fraction of fiber plus the Em, that is the elastic modulus of the matrix. This is a graph that shows the variation of the load carried by the fiber with different fiber volume fraction for varying modular ratio. So, this graph shows that when the Ef by Em is varying, say different, say 1 to 100 or so, and these are the different fiber volume fraction. So, what is the load shared by the fiber? So, we can see that when the Ef by Em is more than 10, as you can see, this is plotted in a logarithmic scale. So, when it is plotted and when the elastic modulus of fiber is significantly high as compared to the elastic modulus of matrix, and with a significant high fiber volume fraction, the fiber carries most of the load of the composite. So, we can see here when this is 10, when Ef by Em is approximately say 10 or so, and the fiber volume fraction is say 0.6 or 0.7, then about 80% of the load is shared by the fiber itself in the composite. So, it is the property of the fiber that dominates predominantly in the composite. So, the load is shared by the fiber and the matrix, and depending on the fiber volume fraction and their elastic modulus, the load carried by the fiber can be estimated. and significant amount of load is carried by the fiber. Now, we will determine the transverse modulus of composite. To determine the transverse modulus composite, here also we will have some assumptions. The first assumption is that there is no separation between the fiber and the matrix, and the fiber composite is subjected to a transverse loading. As we can see here, this is also an idealized schematic diagram of the composite. The two phases, the fiber phase and the matrix phase, are denoted here, and this composite is under transverse loading. So, this is the transverse load applied on the composite. The thickness of the composite is Tc, whereas it is idealized as two different phases, and the thickness of the fiber phase is Tf and the thickness of the matrix phase is Tm. Because of this transverse loading, there is deformation in the composite in the transverse direction, and this is the deformed shape of the composite under the loading. Now, in this transverse loading case, each layer has the same area on which the load acts. So, this means that each layer experiences the same load and the same stress. So, here in case of transverse loading, the composite, the fiber and the matrix experiences the same stress. So, sigma Ct is equal to sigma F is equal to sigma m. Sigma Ct is the stress in the composite in the transverse direction, and that stress is the same in the fiber and also in the matrix. Now, the total transverse displacement is delta Tc, and that is equal to the transverse displacement of the individual phases, that is the fiber and the matrix. So, delta Tc is equal to delta Tf plus delta Tm, where delta Tf is the displacement of the fiber phase and delta Tm is the displacement of the matrix phase. Now, the volume of fiber, that is Vf, can be written as B into L into Tf, where Tf is the thickness of the fiber part, L is the length of the composite and B is the width. Similarly, the volume of matrix can be written as Vm is equal to B into L into Tm, and the volume of composite Vc can be written as Tc into B into L. Now, the total transverse displacement is written as delta Tc is equal to delta Tf plus delta Tm, as we have written earlier. Now, the strain can be written as this epsilon Ct is the strain in the composite in the transverse direction, that is equal to delta Tc by Tc. So, this is the strain in the composite in the transverse direction. So, delta Tc can be written as delta Tf plus delta Tm. So, this can be written as, that is epsilon Ct can be written as delta Tf by Tc plus delta Tm by Tc. So, by multiplying the Tf in the numerator and in the denominator in the first term, and in the second term multiplying the Tm in both numerator and denominator, we get this equation 34, which is written as epsilon Ct is equal to, this is epsilon f, delta Tf by Tf is nothing but epsilon f, and this can be written as again Tf into L into B by Tc into L into B. We are multiplying L into B on numerator as well as in the denominator. Similarly, for this part. So, this is the volume of the fiber part and this is the volume of the composite. So, this ratio is nothing but the volume fraction of the fiber. Similarly, this ratio is the volume fraction of the matrix. So, epsilon Ct, that is the strain in the composite in the transverse direction, can be written as epsilon f into the volume fraction of composite. So, epsilon Ct can be written as epsilon f into volume fraction of fiber plus epsilon m into the volume fraction of the matrix. Replacing strain terms by their corresponding modulus and stresses, we get sigma Ct by Ect. We are replacing here, just see it, epsilon Ct is equal to epsilon f into Vf plus epsilon m into Vm. So, we are replacing it with sigma and E. So, sigma Ct into Ect is equal to sigma f by Ef into Vf plus sigma m by Em into Vm. So, from the equation 37, the relation becomes 1 by Ect, because the stresses are same in the fiber and the matrix and the composite. So, we can eliminate that. So, we get 1 by Ect is equal to Vf by Ef plus Vm by Em. So, this is the equation that can be used to determine the elastic modulus of the composite in the transverse direction. So, it is derived from the elastic modulus of the fiber phase and the matrix phase, and by knowing their volume fractions. So, this equation 38 can also be written as 1 by Ect is equal to Vf by Ef plus 1 minus Vf, which is nothing but Vm divided by Em. So, by knowing the volume fraction of fiber and the matrix and their elastic modulus, we can determine and we can derive the elastic modulus of the composite in the transverse direction. This graph shows the variation of the elastic modulus of the composite in the transverse direction with fiber content. The fiber content are plotted in the x axis, and this is the Ect for different Ef by Em values. So, we can see here that at lower values of the volume fraction of fiber, there is not significant increase in the transverse modulus of the composite. With higher Vf values, higher is the Ect value of the composite. So, the volume fraction of fiber influences significantly the transverse modulus of the composite as well. Now, we will derive the in-plane shear modulus of the composite. The composite element is subjected to uniform shearing and complementary shearing stresses along the boundaries. So, here this is the composite. Similarly, the two phases are shown separately for idealization. So, this is the fiber part and this is the matrix part, and it is subjected to shear forces. You can see here shear stresses are shown. Now, with this shear stresses, there is deformation. This is the overall deformation. That overall deformation of the composite is denoted as delta C, and the deformation of the fiber phase is denoted as delta F, whereas the deformation of the matrix phase is denoted as delta M. So, this is the shearing deformation. The shearing stress in the fiber and the matrix are equal. So, in this case, since it is in plane shear stress, the shear stresses in the fiber and the matrix phase are equal. Thus, tau F is equal to tau M is equal to tau C, which is equal to the stress in the composite. So, tau denotes for the shearing stress. The total shear deformation of the composite can be written as delta C, and that is shown also in the figure. That is, delta C is equal to delta F plus delta M. That is the deformation of the fiber part and the deformation of the matrix part. The deformation of the composite can also be written as the shearing strain into the Tc. that is the, you can see here, this is the total shear deformation of the composite is delta C, and it is equal to delta M plus delta F. So, the shear strain can be written as, that is gamma C is equal to delta C by T C. Similarly, gamma F is equal to delta F by T F, and gamma M, that is the shear strain in the matrix, is equal to delta M by T M. So, we can write that this equation 45, gamma C into T C is equal to gamma F into T F plus gamma M into T M. That is, here we are replacing the deltas with gamma C, gamma and T. So, equation 45 is written as gamma C into T C is equal to gamma F into T F plus gamma M into T M. So, this is written here. Now, dividing both sides by T C, we get gamma C is equal to gamma F into T F by T C plus gamma M into T M by T C, and again we are multiplying the numerator and the denominator with B into L, that is width and the length. We are getting this equation 47. Now, T F into B into L is nothing but the volume of the fiber, and this is the volume of the composite. Similarly, this is the volume of the matrix. So, this ratio gives the volume fraction. So, this is nothing but the volume fraction of the fiber, and this is the volume fraction of the composite. So, the shear strain of the composite can be written as, that is gamma C is gamma F into V F plus gamma M into V M. So, this is the shear strain in the composite. By knowing the shear strain of the fiber and the matrix and their volume fractions, we can determine the shear strain in the composite. So, this can also be written in terms of the shear modulus and the shear stress, that is tau C by G C, similarly for the fiber part and for the matrix part. And since the shearing stresses are same, we can eliminate it. So, we get equation 50, which is 1 by G C, that is the shear modulus of the composite, is equal to V F by G F. This is the shear modulus of the fiber plus V M by G M. This is the shear modulus of the matrix. So, 1 by G C is equal to V F by G F plus V M by G M. So, we can determine the shear modulus of the composite by knowing the shear modulus of the fiber part and the matrix part and their volume fractions. This graph shows the variation of G C with fiber content. Here in the x axis, V F is plotted and this is the G C. Now, with increase in fiber volume fraction, the G C also increases. So, initially the value is quite low, nearly the G M value, but with increase in the fiber content, the shear modulus of the composite also increases significantly. Now, we will discuss the Poisson's ratio of the composite. For in-plane loading of a composite, we have two Poisson's ratio for the composite. One is the major Poisson's ratio, which is denoted as nu CL, which relates the longitudinal strain and the transverse strain. The other one is the minor Poisson's ratio, which is denoted as nu CT, which relates the transverse strain and the longitudinal strain. So, here is also a composite which is idealized as the two-phase system. This is the fiber phase and this is the matrix phase, and they are separately shown here for idealization, and it is subjected to some loading. And because of that loading, there is deformation, and this is the deformed shape of the composite. Now, due to this deformation, the fiber phase undergoes a deformation. As you can see, this is denoted as delta F, and the matrix part also undergoes a deformation, that is delta m. So, from the definition, the major Poisson's ratio can be written as the lateral strain by the longitudinal strain. So, here for the composite, the major Poisson's ratio, that is the nu CL, can be written as the nu CL can be written as nu CL is equal to minus epsilon T by epsilon L. The transverse strain in the fiber and in the matrix can be written as epsilon T f is equal to minus nu f into epsilon L. Similarly, epsilon T m is equal to minus nu m into epsilon L. So, this is the Poisson's ratio of the matrix, and this is the Poisson's ratio of the fiber part. Also, we can write that the strain in the fiber, that is epsilon T f, can be written as delta f by T f, that is the deformation in the fiber by the total thickness. Similarly, epsilon T m can be written as delta m by T m, and epsilon T can be written as delta c by T c, which is for the composite. Now, the total deformation of the composite delta c is the summation of the deformation of the fiber part and the matrix part. So, delta c is equal to delta f plus delta m. Now, delta c can be written in terms of the strain values. So, delta c can be written as epsilon t into T c, which is equal to epsilon T f into T f for the fiber part and plus epsilon T m into T m. Now, we can substitute with these equations with Poisson's ratio. What we get? Minus T c into nu C L, which is the Poisson's ratio, into epsilon L is equal to minus T f into nu f into epsilon L minus T m into nu m into epsilon L. So, we get nu C L, which is the major Poisson's ratio, is equal to nu f into T f by T c plus nu m into T m by T c. Now, this T f by T c is nothing but the volume fraction. We can multiply B into L in numerator and denominator, and this gives the volume fraction of the fiber, and this gives the volume fraction of the matrix part. So, we can write nu C L, which is the major Poisson's ratio, is equal to nu f, that is the Poisson's ratio of the fiber, into its volume fraction V f plus nu m, that is the Poisson's ratio of the matrix, into its volume fraction, that is V m. So, nu C L is equal to nu f into V f plus nu m into V m. So, it follows again the rule of mixture. So, by knowing the volume fraction of the fiber and the matrix and their individual Poisson's ratio, we can find out the Poisson's ratio of the composite. So, this is also as per the rule of mixture. Now, the minor Poisson's ratio can be obtained similarly as, and we can get this relationship: nu C L by E C L is equal to nu C T by E C T. So, the minor Poisson's ratio of the composite, which is denoted as nu C T, is written as nu C L by E C L is equal to nu C T by E C T. By knowing the major Poisson's ratio and the elastic modulus of the composite in the longitudinal direction and the transverse direction, we can find out the minor Poisson's ratio of the composite using equation 59. This is the variation of the Poisson's ratio, the major Poisson's ratio of the composite with fiber content. Here this is the fiber content is plotted in this axis, and this is the Poisson's ratio of the composite. Now, with increase in the volume fraction of the composite, the Poisson's ratio, the major Poisson's ratio also increases significantly. So, this variation is linear. As we increase the volume fraction of the composite, the Poisson's ratio of the composite in the direction of the fiber also increases. So, this shows that the influence of fiber on the composite, the properties of composite can be derived from the volume fraction of the fiber part and the matrix part, and also by knowing their individual properties, by knowing their elastic modulus values, by knowing their Poisson's ratio, we can determine the elastic modulus of the composite in the direction of the fiber or in the transverse direction of the fiber. The fiber volume fraction plays a significant role in determining the properties of the composite. If the fiber volume fraction is high, that means the amount of fiber is high in a composite, the property of the composite also is better. So, the superior property of the composite is mainly due to the amount of fiber present in it, and also on it depends on the elastic modulus of the fibers and the matrix. So, in today's lecture we have discussed the micromechanics of composites and how to determine the elastic modulus of composite. We have discussed the derivation of the elastic modulus of the composite along the direction of the fiber and perpendicular to the direction of the fiber, how to determine the Poisson's ratio and the shear modulus of the composite by knowing the individual properties of the fiber and the matrix and their volume fractions. So, that is all for today's lecture. Thank you.